So yeah, what are scaling relations? You know, when you look at this flow chart here, are processes that ultimately take you from the initial cold dark matter clump ultimately to an observed galaxy. We call scaling relations any of these parameters that ultimately lead to some tight relation, and I can cover that again. I will be sticking mostly with dynamical tracers, and just doing, mostly for the students here, a very quick 2-minute review of what we used to think as scaling relations. For a long time, starting in the 70s, galaxy structural parameters were ultimately based on 3 fundamental ones: size, luminosity, velocity. Out of those, we could build these related scaling relations, ultimately leading to velocity functions. For a while again, most of our studies of scaling relations were based on a few household names: Tully, Fisher, Faber, Jackson, later on, the 7 Samurai. Oh, by the way, I should point out, Alan Dressler here, we're celebrating his career party in Zion National Park, September 2014, write that down. But many people later in the 90s, including many of you in the room here, Avishai, Silk, the Santa Cruz group, many people in Munich, reminded us, largely thanks to the advent of SDSS, that if you don't include more gastrophysics in your models, you're out to lunch. Typically, understanding star formation history, star formation rates, stellar and gas masses are absolutely key in understanding the evolution and scaling relations of galaxies. So again, as part of my introduction, a reminder of where we've gone with these scaling relations. Well, initially, it was literally, as I said, Tully, Fisher, Faber, Jackson, and we quickly realized that these relations could be used as distance and estimator. So that was largely the 70s and 80s. Later on, we realized that we can use these scaling relations to constrain galaxy formation models. And again, many people in this room have been key players, and I should point out the seminal paper by Momau and White, which literally led the advent of a new field of using, pardon? Of, I was many years. Here I'll show your important work as well. But what I'm particularly happy with is the recent development of merging the manifold of spiral galaxies or early type galaxies with late type galaxies into a homogeneous understanding of dynamics of galaxies as a whole. And this is very recent, so I'll mention that very quickly. And Dutton has played an important role. Sebastian Trudeau-Gomez is also in the room, has as well. I will not be addressing the evolution of scaling relations with time. There's yet a new workshop on this that Michele Capellari and myself are organizing, Oxford next year, July 2014. Also write that down. So I'll show 3 recent highlights of scaling relations that I think are particularly exciting. This one here of stellar mass versus halo mass. This is a beautiful compilation. Showing the main sequence of galaxies over many orders of magnitude, which has now become a beautiful challenge for a theorist wanting to understand galaxy formation on galaxy scales and cluster scales. On galaxy scales, this is essentially comparable to saying that stellar mass scales as dynamical mass to the 3rd power. As well, when you look at spiral galaxies and you finally start assembling all the data that were collected in the 70s and 80s, largely for cosmic flow studies, we're able to draw rich, homogeneous Tully-Fisher relations. This is velocity as a function of luminosity, or also size as a function of luminosity. So we're talking about just only a decade ago that we've been finally able to combine all these together. And combining that, the information that I just showed for spiral galaxies, with similar information for elliptical galaxies into, again, a coherent picture of galaxy structure. Here I'm showing what I consider to be a very fundamental slide. It's from the paper of Dutton et al. 2011, although again I'd like to stress similar conclusions were reached by Trudeau-Gomez 2011. And what it shows is that if you look at different halo responses going from standard adiabatic contraction, Blumenthal 86, to potentially no adiabatic contraction or even expansion of the dark matter halo, and you plot against it the offset in stellar masses that's required to match the 0 point of the velocity mass relation, what you find is either for a given model, the late types and early types have obey different relations that ultimately lead to different IMFs in each of these systems. Or if you think that a given IMF applies to all galaxies, then you're stuck with the odd conclusion that galaxies would have different responses to the adiabatic contraction in galaxies. Most of us in this room, I believe, now think that the IMF changes from high mass to low mass galaxies. A third recent realization is still part of my real quick summary, is that n-body simulations are also giving us reasonable galaxies finally. Many people also in this room have been fairly hard on simulators, pointing out that their scaling relations may work in some parts of the parameter space, say Tully-Fisher. I can reproduce a galaxy on the Tully-Fisher plane, but then you would never ever match the other possible planes, such as size, luminosity, star formation rates, abundance matching, and so on. One of the first simulations that finally does it fairly well is this one by Chris Brook. James here is a co-author, and showing you very quickly their success. They are able, with their 4 or 5 simulations, to reproduce the stellar mass, total mass, or Tully-Fisher, baryonic Tully-Fisher, star formation rates as a function of stellar mass. Even H1 is in their simulation, and they reproduce the data, shown here as the small little points, taken mostly from my compilations or Stacy McGaugh, reproducing the data fairly well, with, I must say, for the first time, very little tweaking. But a little bit still. We can discuss that later if you care.
What's going on here?
Well, as I said, let's discuss that, okay? Okay, so let's move on. That's the historical part, the little recap. So why do we care so much about scaling relations? There are fundamental questions that we're all interested in that we want to appreciate. How galaxies acquire their angular momentum is a big issue, and how that angular momentum is distributed between baryons and dark matter particles is key. How various mass components assemble and respond to each other is something that we also want to appreciate. Gas accretion driving the growth of galaxies via minor, major mergers, instabilities, and so on, and particularly how you form bulges and ellipticals is key. And as most of you also study in this room, how do we quench star formation? Well, I'll try to convince you in the remaining minutes that to get there, we need good data. We need deep data, and in particular, homogeneous data. Yesterday, Risa, who's not in the room, showed us that there seems to be, say, in comparing luminosity functions, great differences amongst the well-known luminosity functions. Why does that arise? In my view, it's largely because of issues of inhomogeneity between the different data samples. So let me give you, I wish Risa were here because I just introduced 4 new slides just for her to appreciate this issue, how inhomogeneity will bias your results. So say in the context of Tully-Fisher, some of us realized a little while ago that if you used strictly Sloan data, you'd be brutally biased. Okay, so I would say to all of you, especially theorists, if you get scaling relations that look funny, when in doubt, go to the original data and re-reduce it yourself, or have someone do it for you for a few cases. This is exactly what we did with Sloan galaxies. We picked 3,000 galaxies that already had line widths measured, largely by the group of Giovanelli et al. Accurate line widths, go back to Sloan, take their excellent imaging, but do proper sky subtraction, do your own isophoto measurements, and get, in fact, very different scaling relations. Well, very different. I'm going quickly here, but in terms of the Tully-Fisher, the size, not the size, the velocity-luminosity relation, using Sloan data products will degrade your scatter by 8%. As far as size is concerned, the scatter degradation is as large as 30%. So you better be aware of the data that you're using. Okay, so I invite you to look at this paper here. This is my student Melanie Hall's work. The data are available. This is the largest Tully-Fisher compilation available out there, so ask me for it if you care.
Do you mean it gets smaller or larger?
Okay. So, by degrading, it is larger, of course, if you use, that's what you meant. Sorry, I thought you meant the slope. Of course, the slope is larger if you use Sloan data products. I wouldn't go through all this if we got worse results. So in addition to doing that, then you have to ask yourself, what sort of metric do you use in order to get the best possible scaling relations? There are many different ways to measure a size or luminosity or velocity. A very quick example here, you can use isophoto radii or physically meaningful radius. Here, this is a disk scale length. Tully-Fisher, size, luminosity in both cases, and you can see that the relations that you get are quite different, okay? So again, when you compare that with theory, you need to know how data were measured. All right, I won't go into details, but the point here is that all this comes about largely because, as far as Sloan is concerned, you are now, or our work is concerned, we're now using isophoto fitting rather than slapping a circular Petrosian aperture and doing our own sky subtraction, among others. You can ask also, which is the best fiducial parameter that I should use in my scaling relations, based on the principle that scatter drives this choice. The parameter that yields the smallest scatter is in fact R25 in isophoto radius, and likewise L23.5. Okay, so once again, ask for the data if you care about this kind of data. Now, this is the example to show how homogeneity is so key. Now let's talk about depth. And this now follows the work that Gene and all the people yesterday who talked about slugs and SAGE's results made very clear. We need to go deep. We need to sample the rotation curve or the mass profile of a galaxy. This is an elliptical galaxy here, M105, as deep as we can. Current IFUs, why as deep as we can? Because we, as we discussed yesterday, we really want to know the mass profile of galaxies at all radii, right? Ideally, if we did, we would have a wonderful comparison between observations and theory. For spiral galaxies, we have tracers essentially at every radius. We can't do that with elliptical galaxies because their light profile drops too quickly. So whereas we think we have a good understanding of the mass profile in elliptical galaxies, we don't, even to this day, about elliptical galaxies. How do we get there? This is one example, again, for a well-studied elliptical galaxy and by many different people. And again, you see the different range. This is turning the velocity, the rotation curve, into a mass profile. So we have dark matter fraction versus radius. Perhaps the best radius is up here in terms of RE. So this is going really deep. And yet we see that there's great ambiguity, great noise in the solutions, even at 4RE, 8RE, and so on. We would like a low scatter in this plot here that enables us to say our galaxy's maximal. What's the fraction? Is it 50%, 20%, 40%, and so on? On this particular plot, I should show the old Capillari 2006 result, about 0.3. And I should point out that if we compared with spiral galaxies, typically spiral galaxies tend to be more dark matter dominated than the inner parts. This is a typical locust. Okay, something like 50% all the way up to 70% dark matter dominated, okay? So how do we get there? I'll show in a few minutes that I'll discuss, and you know that most of the available IFUs are quite small in field of view. There is no way with current technology that we can push, with IFUs, that we can push beyond 1.5 or 2 REs. That was well discussed again by Gene and collaborators yesterday. And short of having distant tracers, one avenue is to use long slit your good old long slit on big telescopes, where can it lead you? So now I'll introduce two projects really quickly. This is the SHIV survey, which stands for spectroscopy and H-band imaging of the Virgo cluster survey. With long slit, I'll convince you that you can go very far. You can't go as far as using planetary nebulae and globular clusters, but you can have very large samples. So in this case, SHIV is a project that started with H-band imaging in Hawaii at CFHT and University of Hawaii as well. It's completed. This was the thesis of Mike McDonald, who's now at MIT. With that part of the survey, we showed the very interesting result that galaxies and clusters, or at least in Virgo, come in a bimodal distribution of surface brightnesses. This, by the way, this result, which was challenged by many, has been corroborated using Spitzer data by other teams. So it's still something that we need to understand well theoretically. But the and Joel Roediger in his next talk will talk about using the optical and infrared parts of this survey to study stellar masses. My student Nathalie Ouellette is in charge of the spectroscopy of the survey. For about 4 years, we collected long slit profiles, rotation curves, and velocity dispersions at Palomarket Peak and Apache Point Observatory for about 200 SHIV galaxies, and I'd like to show you some new results. Although first, just point out that the data we get are definitely deeper. Some of you in the room may know CALIFA. This is a survey at Palo Alto using an IFU of nearby galaxies. I'll describe it in a few other slides. It gives you beautiful resolution in the inner parts, but again, the advantage of the long slit is the field of view. Typical IFUs now on 4 or 5 meter class telescopes will give you an arc minute or so of field of view, which is much too small for nearby galaxies. With the long slit, you can go much deeper, mind you, not with the same spectral and spatial resolution. All right, so Jean talked about the full range of V over sigma that galaxies in their sample showed, and this is definitely borne out with our data. I'm showing you here sigma as a function of r, and note this is the r over re going out to 6, 4, 5, 6. This is awesome. We're able to beat the 1 to 1.5 re wall that's been hitting us for so long, and at the price, mind you, of exposure time. The great range, this sigma, by the way, this is an RMS sigma, so it's v squared plus sigma squared, okay, square root. So it's the full I didn't have time to do the v over sigma. I can show you. But there is indeed a full range of mass profiles for elliptical galaxies. And I want to stress again, that's the take-home point, I suppose, that it's shocking that in this day and age we still don't have a good view of elliptical or early-type galaxies as we do for late-type galaxies. Right? If someone asks you in Astro 101, what's the rotation curve of a spiral galaxy, boom, you know how to draw it. Draw the same thing for an elliptical galaxy, and you don't know, right? So, and especially given the fact that there's a component of it that's ordered and random. Moreover, if you're interested in fundamental plane studies, because now we can go beyond this, right, let's backtrack. Early fundamental plane studies basically use the velocity dispersion at the center of the galaxy sigma naught. As we go further in galactocentric radius, which we do say here, this is fundamental plane for versus radius here, sigma naught, RE over 4, 1.5 RE. As you go deeper and deeper, you find that your scatter gets smaller and smaller. No one has ever done a fundamental plane extending beyond 1.5 RE. 2 perhaps really keep on reducing as you go. For theorists, this is very important. So, I should say here, we've exhausted the benefit of 4 or 5 meter class telescopes. We can't go beyond. We've gone as far down in the luminosity function as we could, and we're now pushing for 8, 10 meter telescopes to finish the survey with 2 fainter galaxies. All right, so let's wrap up with a parallel with the high redshift universe. Reinhard showed us beautiful data, the continued extension of their work with Natasha and others based on VLT Symphony. What we need, mind you, is always a foil at low redshift. Okay, so what is going to be this survey at low redshift that truly complements what we find at high redshift? Well, there are a number of projects that are ongoing. Don't have time to describe them in detail. Disk mask, this is based on Calar Alto. Solar and Atlas 3D has been perhaps the most successful of them, yielding beautiful V over sigma profiles for about 300 nearby elliptical galaxies. Khalifa as well, SAMI in the south at AAO. These are wonderful and definitely starting to approach the size that we want. However, again, appreciate that their field of view is very small. We're talking about 1 arc minute. And 1 arc minute doesn't bring you in the range where you need to see profile variations. So my last couple slides are about this new program at Sloan, MANGA, that will start next year, which will provide deep, well, fairly deep, dynamics for V, sigma, dust, metallicity, stellar masses, and so on. Again, though, out to 1.5 RE. So hopefully you read with the rest of the slide. No, I should go back. MANGA starts next year and will be online for about 6 years. First press release and data release in 2015. So this is what Sloan has given us. A 3 arc second, spectroscopically speaking, a 3 arc second fiber on most galaxies. This is what MANGA will give us. Okay? Now that's cute and it's impressive, and finally we have 2D information about all the dynamics of galaxies. However, again, we appreciate that MANGA suffers from the same problem that these other surveys also suffer, from small field of view. So until we can build really large IFUs, the solution, the complement to these is SHIV or similar programs based on long slit on very large telescopes. All right, so to conclude, the wish list for scaling relations of nearby galaxies based on optical dynamical tracers is to go deep and homogeneous, okay? And in particular have measurements of V and sigma that are well understood. I didn't talk about distances. Accurate distances are also important for this game. Baryonic Tully-Fisher and fundamental plane analyses will benefit tremendously also from multi-wavelength studies, something that Linda also addressed in her talk. No time to go over this, but the multi-wavelength multiplexing also with IFU and long slit data will be a true game changer in the next couple of years. So I'm just going to flash the science questions that I showed earlier as way of conclusion, and I will conclude right here. Thank you.
Your last point there, you really would like to have, so to speak, an equivalent.
This one.
Low redshift and high redshift. Are you concerned that MANGA does not have the spectral to get sigma, a little sigma there, at least in the gas component, but maybe even in the stars, well enough that it really is constrained?
Well, you sort of put the answer in the question, do you? Yeah, MANGA will not do as much as we wish it will. I think Khalifa is currently delivering what we really want in terms of spectral resolution and spatial resolution, mind you, for a smaller sample. So MANGA is not ideal. Absolutely not. Here I have, let's flash this slide again. This is what you're alluding to. So the spectral resolution in this range is indeed not small enough. So, but that's why the complement to doing long slit on very large telescope is absolutely key. The problem there, and the reason why it's taken so long to acquire the data, as you know, is the integration times per object are too long. We cannot multiplex. We don't have IFUs to deploy. We must do one galaxy at a time.
You guys should do it right and build a new spectrometer, which you would do with this project, and have the right resolution.
I will talk to you privately about this, because it's been years that I fight for something like this. I don't want to, you know, I'm part of manga, and it's going to be great for what it does, but it will not, something like SHIV on large scale is truly what's needed. But SHIV has already taken 4 years, and doing long slit on galaxies is not very time efficient. So, Duncan.
Multiple position angles, or is it just along the major axis?
Right now, SHIV is strictly major axis. But you're right, we'd like to have 1D minor axis. However, most of the comparisons with IFU data, say Khalifa, show that 85% of the time, the sigma 1D is very similar to sigma 2D. And definitely, as you know, for velocity, for circular velocity, major axis is fine. You don't need, it's really for non-axisymmetric perturbations. And right now, as you gather, my focus is largely on early type galaxies. The spirals are understood, they're good. I think, the non-axisymmetric perturbations in early types are not as prevalent as they are in spiral galaxies. So we're in good shape.
David?
In your original list of parameters that might be relevant for scaling, you had blocking winds, but those are your science questions. You do not include outflow, you know, they would obviously affect angle momentum. So did you purposely not include them?
No. Outflows and winds. I mean, again, this is there where I started doing winds with Sylvain Veilleux 10 years ago, and they were so complicated, I just dropped out, but they're fundamental. Yeah.